I welcome back all the participants to the session 3 of day 4 Auto-led DP on application of AI, ML and DL in smart healthcare, organized by Department of Computer Science and Engineering of Maulana Abul Kalam Azad University of Technology, sponsored by AICTE ATAL. It gives me immense pleasure to welcome and introduce our eminent speaker, Professor Nandini Mukherjee ma'am, associated with Jadavpur University, Kolkata. Professor Nandini Mukherjee ma'am received the PhD degree in the computer science from the University of Manchester, Manchester, UK in 1999. She was the recipient of a Commonwealth Scholarship for her doctoral study in the UK. She has been a faculty member with the Department of Computer Science and Engineering, Jadavpur University, Kolkata, India since 1992, where currently ma'am is a professor. Before joining academia, ma'am served in industry for nearly 3 years. Ma'am has served as the director of the School of Mobile Computing and Communication, Jadavpur University, for almost 6 years. She is an active researcher in her research areas, which currently include high performance parallel computing, grid and cloud computing, and wireless sensor networks. Professor Nandini Mukherjee ma'am has authored more than 150 research papers in international journals and conferences. She has also been involved with the organization of several international national level conferences, workshops, and seminars in various capacities. She is a senior member of the IEEE Computer Society and member of ACM, and also enthusiastically involved with Free Software Movement of India. The talk will be delivered by Professor Nandini Mukherjee ma'am is on big data, artificial intelligence and healthcare, some experiences. Before I request ma'am to take on this session, I would like to highlight the abstract of the talk. The abstract is, in the era of Internet of Things, huge amount of data are generated by the sensors, which distributed over a large geographical area and continuously sensing the surrounding environment. Healthcare is one such domain where sensors can be effectively used for sensing important health parameters of patients. This health data has every attribute of big data, that is volume, variety, velocity, and veracity. This data needs to be processed in real time to meet the requirement of critical health conditions. However, several challenges come up while working with health data. These challenges include how to represent and store this data for efficient retrieval, and how to overcome the uncertainties in data contributed by inaccuracies of sensors. In this lecture, some practical experiences of working in IT-enabled primary healthcare will be shared, and how simple AI techniques have been used to overcome the challenges will be discussed. Now I requesting ma'am to take on this session. Over to you, ma'am. Thank you.
Thank you, Rupali. Thanks a lot for introducing me and just briefly giving the overview of my talk. And I also thank Shuparna and other organizers of this particular program for giving me the opportunity to share my experiences. I also thank MacOut for arranging such a nice program, particularly in this particular area. As Shubhupali has already mentioned, my talk will be on big data, artificial intelligence, and healthcare, some experiences. So you are actually listening to this, to different speeches from different eminent persons for the last 4 days. This is the 4th day and last session, right? So during this last session of the 4th day, I'm not going to discuss any sophisticated algorithms or complex techniques. I'm not going to discuss all these things. I only focused on the actual problems which we faced when we worked in a particular project in this domain, primary health, in this domain, healthcare, and mainly how we tried to overcome. And that will be in the discussion, included in my discussion, right? So let us start with the state of healthcare in our country. Our country is very large, and obviously all of you know that currently 1.3 billion people are living in India, and the population is increasing. The population of elderly people is also increasing. Okay, so we have 48 doctors per 100,000 persons, 1 lakh persons, right? Which is much lower than developed countries. We have really scarcity of, we are facing scarcity of doctors, okay? And then also, we have only 1 million doctors, and among the 1 million doctors, only 10% of the doctors, they work in the government hospitals. There is a huge gap between urban and rural areas regarding when we talk about availability of medical services. Okay, there are about 4 times as many trained doctors per 10,000 population in urban areas as compared to the rural areas. So rural areas, you know, in most part of rural areas, we really do not have any healthcare facilities. Okay, and even in many of the, wherever we have government institutions, there also the facilities are very poor compared to corporate hospitals. And in corporate hospitals also, we must say that always we do not find very good healthcare services, right? So with all these problems, we are in this talk, I'm trying to focus on primary healthcare. Okay, why are we talking about primary healthcare? During the last 4 days, perhaps you have learned much of the machine learning techniques for solving very complex problems in healthcare domain. Okay, it's really there, the healthcare, the IoT-based services, the ML-based services in healthcare, those are gradually increasing and getting much focus from computer scientists and scientists in other domains. But primary healthcare is also very important because it is the only practical course of action to address the problems of malnutrition, child death, and illness causing diseases in India. In fact, you know, when we faced the first and second wave of COVID-19, all of us know that how what were the problems in all over India. Really, there were almost there were no doctors, no treatments. So something went like that. Okay, so primary healthcare is really really a particular area where we need to focus. Okay, so primary, in addition to that, primary healthcare provides good health to the community as a whole, not just to individuals. If we consider corporate, private hospitals, or maybe super specialty hospitals, then the healthcare is for individuals. But when we talk about primary healthcare, that provides good health to the community as a whole. Okay? So other problem is when we who live in the urban areas, we see that patients directly come to the secondary health centers for very simple problems, which could be cured in the primary health centers if we had that type of facilities. So such type of activities by the patients, that means going to the secondary health centers directly, this is creating enormous pressure on the hospitals. If any of us go to the government hospitals, we will see that there is enormous pressure. Doctors are just running around, nurses are running around, people are running around, really to provide services to large amount of people, a large number of people. Okay, so these things could be tackled in primary health centers if we could provide that type of facilities. Also, primary healthcare helps to create healthcare centers help to create awareness of viral diseases. For example, even if we had that type of facilities, we could provide awareness during the COVID-19 first and second wave, and even now, sanitation practices and family planning, all these things could be handled if we had that type of facilities. In fact, we have also examples that how primary healthcare centers effectively removed some of the diseases like polio, etc. Right? So we actually worked in a project, remote health project, under this was funded by ITRA, Information Technology Research Academy, by MITI, Ministry of Information and Electronics Technology of India, so Government of India. So this was funded by MITI, and we worked for almost 5 years under this project. Obviously, it was a 6 institutions project of 6 institutions. That means 6 institutions collaborated. Jadavpur University was the lead institution of this project. So, objective of that project was provisioning low-cost, on-demand, and secure healthcare services at remote locations using sensor, mobile, and cloud technologies. Right. So, the idea is like this: doctors are remotely located. Health workers are trained to take patient history, note patient complaints, and make clinical examinations. I will explain this in more detail later. Communication happens over the internet. Communication between the doctor and the patients and the health workers would have happened over the internet. Okay, so whatever I am going to discuss in my few next slides are actually drawn from the experiences which we gathered while working this remote health project, right? So, and as I said again, we will mainly focus on primary healthcare. So we have taken few usage scenarios. The first one is continuous monitoring of elderly patients or patients on move, right? So many of us understand the technologies used for this continuous monitoring. Kiosk-based healthcare delivery. I will talk more about kiosk-based healthcare delivery in my next few slides. Also, one of the usage scenario when we work in remote health project, how to store data. Basically, it is a challenge. How to store data efficiently for future use of healthcare services. That means it is not just real time. You are treating, the doctor is treating the patient, giving the prescription, and then just that particular part of the treatment is forgotten. It is not like that. We need to store the data somewhere efficiently for future use, maybe by the management, maybe by the administration, maybe by the country as a whole. Okay, so we need to store the data efficiently. Also, provisional diagnosis of diseases by analyzing health data and user queries. So perhaps in all cases, the doctor's intervention may not be needed. In certain cases, provisional diagnosis could be made by analyzing health data and also discussing with user. I will again talk more about this particular use case 4, right? So these are the 4 use cases which we considered to be effective for our primary healthcare services. So with this understanding, we actually proceeded for setting up kiosks in the villages of West Bengal. There had been some more such projects in all over India. You might have heard about such projects in other states as well, in our state as well. But what was additional in our particular project, that the research component which we added for while working this particular project. I will come discuss those things. So this, the idea, what we did, we have set up. You can see the kiosk here. This kiosk was set up in the Bankura district of, in the Birbhum district of West Bengal. The village name is Borra. So there actually we recruited some of the village girls who were trained to examine the patients using some sensors. You can see the village girls, they are examining the patients clinical, they are performing the clinical examinations, and then they can use the tabs or laptops or such type of mobile, devices, computing devices, small computing devices, even smartphones they can use, and those data are transmitted to our cloud environment. So this cloud environment, that we either transmit sensor data directly, or the health workers input the data transmitted to the cloud environment. The urban doctor is sitting, the doctor is sitting in a remote area, preferably in the urban location. At the urban location, the doctors can see the data. If the doctor wishes, the doctor can also chat with the health workers or with the patients, and then the doctor sends the prescription to the cloud environment, and that comes to the patient for further action. The doctor can also suggest some lab tests, some pathological tests, some examinations, etc. So there can be several such options. So you see, in our this particular approach, we did not exclude the doctor. Although provisional disease diagnosis can be made, but in this particular approach, we didn't exclude the doctor. Rather, doctor is remotely located, and we just send all data to the doctor for his or her perusal and or analysis. Okay. So this is the scenario, and as I said, this particular whatever the software which was developed under this particular project not only performs this job, along with that, it can also monitor the patient who is either on move or maybe again at another remote location where continuous monitoring is needed. The data can be used by the hospitals, maybe specialty or super specialty hospitals. The data can be used by the administration, like state administration or central administration, for taking any action. That means, suppose when if the disease is spreading in one particular area, the administration should be able to take certain actions. So this was the plan, and in fact, again, I'm giving example of the this COVID-19 this time. Perhaps at one particular time, the doctors were not available at all. So some on-call visit systems were developed by several app developers. Okay, and those visit systems also worked, right? So in our case, what we tried to do, we again, as I said, it's not just developing a soft piece of software or developing some apps, rather to progress the research in this domain so that the problems or the challenges faced to implement a particular this type of setup can be overcome. Okay, so I will mainly talk about the challenges which we realized that challenges which may evolve while implementing such type of setup, and also I'll just give some hint how we tried to overcome these challenges. obviously there are a lot of research scope. If you are really interested to work in this domain, there are a lot of research opportunities which really have not been solved till now, right? So what are the requirements? The requirements, when we analyzed at the beginning of the project, when we analyzed what are the requirements, we have seen, we understood that we need an infrastructure for remote on-demand services. Continuous event-based monitoring of health parameters, okay? Structured and unstructured data generated in huge volume. We will talk more about data generated from this remote health solution. And in fact, for any kind of healthcare services, real-time data processing and correctness of data. This is very important. I will more focus on correctness of data, because data actually, particularly when we talk about health data, correctness is very important. See, when we measure environment temperature, if it is 40-degree actual temperature and for some reason, maybe for instrument error or maybe for other reason, actually you measure the temperature as 39 degree, really doesn't matter. But when it is regarding health, then if you measure, if actual temperature is say 101 degrees Celsius and you measure 99 degrees Celsius, then really that matters, right? Even 1 degree, 2 degree difference matters when we talk about healthcare. There are other clinical parameters also which really matter. So so whatever data we gather, those should not be erroneous. We need to handle the correctness or accuracy and preciseness and also uncertainty of data. So in infrastructure, when we talk about infrastructure, we found cloud-based service deployment is the best if we can maintain the privacy and security. I hope Professor Shormishta Niyogi already talked about these things. In fact, she was and Professor Shomiran Chattopadhyay both were involved with our project. So cloud-based service deployment is obviously one of our solution, provided we have privacy and we can implement privacy and security here aspects. We can take care of privacy and security aspects here. Continuous event-based monitoring of health parameters. This is again another requirement where e-health sensors could be attached. W-band wireless body area network can also be attached, which should have communication capabilities over the internet. Regarding structured and unstructured data, we propose to use semi-structured databases. In fact, we are using MongoDB at this moment, but we can also try other semi-structured databases. Real-time data processing, for this actually your whatever algorithms, whatever you use, that those should be lightweight. So that is the prerequisite that you, whenever you develop any algorithm, whatever, those should be lightweight. Okay. Correctness of data, for that we can use some AI techniques. I'll just show some simple techniques, but obviously you can think about more. Okay. So while talking about cloud environment, you see, this is cloud. I think all of you know this is a cloud environment where, I mean, just a graphical representation of cloud environment where we have different components. For example, we have compute devices, block storage devices, network devices. On top of that, we can build infrastructure as a service or IaaS. Similarly, we can also build platform as a service, and also we can build, if we provide software services, then we can also build software as a service. So when we have such cloud environment from external, as external users, we can communicate with the cloud environment using our laptops, our mobiles, our smartphones, our desktops, our servers. So in whatever way we want, we can communicate with the with our cloud environment. Okay, so this is something which is well known to us. Now, currently, you may ask one question that, okay, connecting sensors to the cloud is easy, just like we connect laptops or mobile phones with cloud. Why don't we connect sensors, and probably we can use a mobile phone as a coordinator or as a gateway with the sensor network and directly transfer the data to the cloud environment. It's very easy. And in fact, a lot of people have done this. Okay, that's true. A lot of people have done this. But then again, we have, whenever we do this, we faced several challenges. What are the challenges? See, sensing devices, we have heterogeneous types of sensing devices. We have Arduino boards, we have other type, Raspberry Pi, we have other types of small devices, we have small sensors, several types of several types of interfaces, with several types of communication interfaces as well, and working with several different communication protocols. Okay, so these are the challenges. How do we get data in similar way from such type of sensing devices? Should we develop different apps for different devices, or should we develop an app which will be able to communicate with all these devices, all types of communication protocols? Then that means the app itself will become heavyweight. So how to overcome these two challenges? Then there is another aspect, which is we may need to share the data stream. For example, when we have one particular sensor, from the sensor, the data may go to the doctor. The data may also be recorded one of the storage spaces, or maybe on a server of belonging to the administrator, or on a server which is located in Shastro Bhavan of any of the state, so that they can analyze the data. So there may be several such uses of the data from the same sensor device. So how is it possible to share the data streams from a sensor device without developing a different apps for different devices, for different such type of services? Is it possible? So that was another challenge which we considered. And there are more challenges also. I'm not going to talk about all of these challenges. So we decided, why not we develop some of the systems, so that the sensors or sensor networks, they themselves become a component of the cloud itself. That means just like we shared the compute devices, in the similar manner, we would say share the sensors or sensor networks as well. So why can't we do that? So we just modified the NIST definition of cloud slightly. I hope all of you know the NIST definition of cloud. Cloud computing, this is a model for enabling convenient on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. So this particular definition, we just changed and added a little, I mean, only 3 words. We added sensing and storage resources. So now the sensing resources also became shareable, a shared pool of configurable computing and sensing. Okay, so shared pool of configurable resources. Sensing resources have also become shared pool of configurable resources, and they can also be rapidly provisioned and released with minimal management effort or service provider interaction. So we changed the definition and we introduced virtual sensor, which is a software abstraction that allows sensor data streams from one or more heterogeneous types of sensors to be shared among different applications, right? So they allow sensor data streams from heterogeneous types of sensors, and those data streams can be shared among different applications, okay? And they can also be, either they can be shared individually or in combined manner. And we can also apply some pre-processing techniques, like we can apply some fusion aggregation algorithms as per the application requirements, okay? So smoothing analysis, what type of function you need, you can always apply on top of the virtual sensors. So this was, again, virtual sensors were introduced prior to our work as well, and many researchers, they work on virtual sensors, but obviously our proposal for virtual sensors are a bit different. We first categorized them, and also we generated, I'm not going to talk about virtual sensors in detail, but we proposed certain scheduling techniques, and also how do we acquire the virtual sensors, how do we release them. So for all this, because they cannot be acquired or released in a similar manner like computing devices, there are some differences, but we tried to overcome all these challenges, and we tried to solve many of the issues through our research, okay? So I said we categorized. So categorized means we just define. Here are some mathematical definitions. Again, I would not explain all of them, but some of them, as you can understand, singular means that means these show the relationship. All these expressions show the relationship between a physical sensor and a virtual sensor, right? So between a set of physical sensors and a virtual sensor. So these expressions show just the relationships. So singular means there is a one-to-one correspondence between a physical sensor and a virtual sensor. Selector means we have a set of physical sensors. We just select one of them for giving data. Okay. Accumulator means we have a set of physical sensors. We take all the data from those sensors. Aggregator means we run an aggregator function to aggregate the data from a set of virtual sensors. Similarly, we have qualifier, context qualifier. Here we try to predict, applying AI techniques, we try to predict any missing data, and also we try to compute some values. Again, here we can apply some AI or ML techniques just to compute. Okay, so these are the IAS level sensors. These are the PAS level sensors. We introduced these categories, and we developed this layered architecture for virtual sensors. What is the proposal? See, we can have the architecture is general enough so that it can handle applications in healthcare as well as environment monitoring or other applications, right? So we can have different types of user applications. Okay, now we can have WSNs for environment monitoring, wireless sensor network. So suppose we have a WSN deployed in a forest to detect forest fire. We can also have sensors fitted on the human body, right? They can be individual. Generally, sensors which we fit on human body for some continuous monitoring. In most of the cases, they are individual sensors. For example, blood pressure sensor or ECG sensor. But obviously, you can also have a body area network fitted on the human body. That also possible, right? So from these physical sensors, we create one level of the first level of virtual sensor in some of the edge devices. Obviously, we can eliminate this layer as well because they are always not essential. We can directly send to cloud at some data center. But here again, we can create virtual sensors in the edge devices as well, which we term as cloudlets. Okay, these cloudlets here we perform these tasks on virtual sensor: creation, aggregation, filtering, and error handling. Okay, and then and as you can see the names, this accumulator means it will take all the data from all these devices, accumulate here, and will send as a single piece of data to the cloud, right? So again, we have qualifier, which will take one single data. We also have aggregator, which will perform some aggregation function over the data, etc. And here we create at the IAS level, we create the second level of virtual sensor like VS1, VS2, etc. Here again, we can create, aggregate, filter. This particular level also takes care of mobility, right? So mobility management is also possible here. And in certain cases, because we want to share, so we can also create a clone of the virtual sensor, which will send data to two different applications. For example, here VS4 is sending data to two different applications. Okay, so from at the past level, we just perform the association. That means this application will be associated with VS4. So this application this application will also be associated with VS4. So these two applications, they don't need to know the details of communication protocol, hardware details of all these sensors. They will only know about this virtual sensor, which they will just like our computing resources. In case of computing resources in cloud, you do not need to know the configuration of a server. You only request for 2 CPUs, 4 GB memory, and something like that. Okay, and maybe Linux operating system. Here again, you would request for an accumulator doing such and such, performing such and such functions. Okay, based on the maybe an accumulator for measuring blood pressure and body temperature of a patient. Okay, so that will be the responsibility of these edge devices or the cloud to create to acquire such type of sensors and then accumulate the data and then send to the application. Just one thing we need to be careful here. See, when we talk about healthcare, that is different from environment. In case of environment, you can identify the location using GPS, latitude, longitude. In case of patient, similarly, we need one ID. So we are using specific ID of the patient. Otherwise, it doesn't mean anything to the doctor. So unless you associate an ID to each patient, this particular system will not work. Okay, so we also have such type of system to associate an ID with the patient. So I have just given some concepts of virtual sensor which we have used or we have developed under our project, and here are the publications which you can obviously you will be able to find in the wherever they have been published, and you can go through for further details. Okay, right. So next, after introducing virtual sensor, I would talk about healthcare data, especially primary healthcare. What type of data we actually work with? Is it only sensor data? No, there are other types of data also. Although my focus will be mainly on sensor data, but we cannot forget other types of data also. They are also important. Okay. For example, when we work in primary healthcare, when we tried to, when we developed our kiosk application, we have developed one kiosk application which has worked, under our project for several months, right? So what kind of data we needed to obtain from the patients? The first is demographic data, the address, location, etc. Other type of data. History data like family history, past disease history, allergy history, etc. Clinical parameters. Here we used sense data, but other types of data as well. In fact, I will talk about other types of data next. So other types of data as well. And we had to do some, health workers had to do some clinical examinations. As I said, they were trained to do that, simple examinations. For example, whether the patient has anemia or not, right? Whether the patient has certain, anemia, checking anemia is not very difficult. So how deep is an injury, right? So such type of clinical examinations, the health workers, the rural girls, they can perform and they can communicate that to the doctor. Now, this is the name of the application, KIOR. So we work with this KIOR application, kiosk-based rural healthcare delivery. So here, that means because we have all this data, what I discussed here, because we have all this data, so there are two parts when we talk about data. First part is clinical data acquisition in using sensors. That's the first part. Second part is, other than demographic data, history data, we also have CDSS-based symptom acquisition. Again, when we talk about AI, CDSS is a simple AI-based technique for healthcare delivery. It's not always simple, and so I'll come to CDSS right next. So clinical data acquisition using sensors, we could use all these sensors. They are available from several manufacturers, vendors. Obviously, there are several competitors in the market, but all of them are not very good, unfortunately. Those e-health sensors which you can use for your research may not give you accurate data. And doctors, sometimes they do not rely on these sensors. That was one unfortunate situation faced by us. Unfortunately, there are other sensing devices which are available in the market, but they are proprietary. That means you won't be able to use your own code with such type of sensors. These sensors which you use, which you can use for your research, and they are not, sometimes they are not reliable, but the sensors which you can rely upon based on doctor's opinion, they do not allow you to run your own code. So that's a problem. I hope this will be this problem will be overcome sometimes in future when research in this domain will increase. So here are some of the examples. We used sensors from Cooking Hacks. Cooking Hacks, mHealth sensors, they provide. Also, in some cases, we used Arduino boards as well, purchased the sensors from the market and fitted those on the Arduino boards, because Arduino board has the communication facilities, right? So when we perform clinical data acquisition, then that part is with our virtual sensor. When we deploy the virtual sensor on our mobile device, that can accept in this manner and send that to the through the cloud, as I have explained a few minutes back. Okay. But more importantly, when we, in this particular talk, I focused on clinical decision support system, because this was also an important addition with our work. Okay. So what is clinical decision support system, or CDSS? there are two categories of CTSs. The first category, it can be knowledge-based. That means just the knowledge, expert knowledge, domain knowledge can be stored on a storage device. In our case, maybe cloud, maybe in cloud. If then rules are created, that means if this is this, then they do this, something like that. So system retrieves data to evaluate the rule and produces an action or output. Rules can be literature-based, practice-based, or patient-directed evidence. In our case, the doctors, expert doctors provided the rules for us. Okay. Obviously, there are non-knowledge-based CTSs. In fact, whatever I hope you have learned during the last 4 days, those were mostly non-knowledge-based CTSs. Probably you can say non, because the decision depends upon the machine learning or statistical pattern recognition techniques. Okay. However, in these cases, understanding the problem is a challenge. Unless you understand the actual clinical problem, how would you implement statistical pattern recognition or machine learning? So that's a problem, and you need experts' help for that. Also, there are problems with data availability. While working with such type of non-knowledge-based CDSs, you need experts here in this domain. And unless you work with some doctors, it's never possible to find anything from this. Okay. So here are some figures explaining knowledge-based CTSs and non-knowledge-based CTSs. You can see the knowledge user, that means us or maybe the patients or maybe the health workers. They communicate with the interface engine. Here we have the knowledge base. The user choices the clinical data comes here, come here and ported to the inference engine. The inference engine then finds the recommendation and sends to the user. Okay, I will explain how we did this. Obviously, we had the knowledge base here. I have only a very small sample of this knowledge base. Non-knowledge based CDSs, the same thing, but only the inference engine has become AI powered, and we can run algorithms. For example, whatever algorithm you want, you learned in AI or machine learning, you can place here. But you still need the clinical data. So CDSs can be used for several in several places. For example, we can make diagnosis of the diseases. That's possible. But as I said, we did not exclude the doctor from our loop. It can generate alarm systems for the nurses or for the healthcare workers. Disease management is possible. Prescription generation, drug control, and we can write many more. So CDSs has many scopes. Okay. Here is an example which you can see from this paper. So based on a graphical user interface and a fuzzy logic controller with rule viewer for identification of the type of peripheral neuropathy, right? So there is an integrated medical records database. The system could take inputs in 24 input fields for clinical values of the diagnostic test and clinical symptoms. So it will ask questions, and based on that, you will have to put input in 24 fields. Okay. Output field is the disease diagnosis. For example, it can diagnose motor neuropathy, sensory neuropathy, mixed type, or a normal case. Okay, and such system obtained 93.27% accuracy. So, sorry, this I found in the literature. Similarly, again, an interventional CDS for image ordering developed at Virginia Mason Medical Center. So that was shown to decrease the rate of lumbar MRI or low back pain for low back pain, head MRI for headache, and sinus CT for sinusitis. Okay, so sorry, sinusitis. Here you see this imaging that if you use imaging, that means a lot of image data. Those will aid radiologists in selecting the most appropriate test to run, provides reminders for best practice guidelines, alerts for contraindications to contrast. Okay, so there are many such works which you can find on the internet or any research domain. So those were based on the use of CDSS. Our work, again, it is knowledge based, but as I said, we focused on primary healthcare only. So we again have a knowledge base. How we stored the knowledge base, I'll discuss that. But it asks questions like this. Say the patient complained about, so we would ask what is the first complaint, first symptom of the patient, the main symptom. Okay, so say patient said pain. So where is the pain? Headache or ear pain, teeth pain, etc. So headache pain. And then these questions, because pain, headache, pain, and headache. So these questions will be asked: duration, where did it start, so etc. So how did it start? So all these questions will be asked. Okay. Now suppose the patient says pain and vomiting, right? So pain, we ask several questions. For vomiting, again, the question will be changed. Here you see we could ask what are the frequencies, what is the appetite, what precipitated it, etc. And there are possible answers also. And based on that, you see we have rural girls who are health workers, so they don't have clinical knowledge at all. Okay, we just trained them for certain things, but apart from that, they won't be able to do anything. So all these questions are questions and answers are given to the health workers in the form of if-then rules, and they would just supply the answers to this. So according to us, this is the whatever systems we have seen in other places, such type of system is not available with such type of knowledge-based system for primary healthcare. For other domains, certainly we have such systems, but for primary healthcare, we don't have such type of systems. But you see, once you know, so these are the symptoms. We divided symptoms in three parts: main symptom, subsymptom, and related questions. Okay, and there are multiple choice answers for each question. These symptoms are stored as tree structure in JSON format. Now you see, when we talk about such type of if-then rule the questions, etc., you may say that it's easy. An app can be developed very easily when we work with such type of when we have such type of knowledge base. But again, we have some challenges. How to store the knowledge base and where to store the knowledge base? The answer to the first question I have already given. We stored the knowledge base in tree structure. In fact, I must say, not as a tree, as a graph, as you can see the graph. So this is a graph, this is a directed graph and acyclic, but we named it as disease symptom graph. Okay, why it is not tree? Because we may need to start from different symptoms, multiple symptoms. So we have symptom nodes at the first level. Okay, then we have many sign of symptoms, symptom nodes, based on which we ask questions. Okay, and then we have the disease nodes here. So symptom nodes, sign of symptom nodes, and disease nodes, right? So we we named it as a disease symptom graph, and you can see they have directions like this. we can reach to a disease from different symptoms, through different paths. We can start with multiple symptoms. So these things can happen. Using such type of graph, if the graph is very good and do not provide any ambiguous answer, then obviously that means our knowledge base is very strong, then provisional diagnosis is possible using this type of graph. But obviously, usually we do not work with a very strong knowledge base. Therefore, always it is whatever we get, the disease may not be, or sometimes the patients, they do not give proper answer. So then we need the doctor. So if we cannot, we didn't try provisional diagnosis, the doctor was always there. But if but we can embed provisional diagnosis system also with our software. If provisional diagnosis can be done, then obviously that would be the answer. If provisional diagnosis cannot be done, then that can be referred to the doctor. So this will also reduce some pressure over the doctors and over the hospitals. Please let me know if there are any questions. But the participants may ask questions if it is required.
Yes, ma'am. But till now, no questions. Participants are requested to please post your questions. Or ma'am, at the session, they can unmute themselves and ask, or they can post in the question answer area.
Sure, no problem. Thank you. Okay, so here is an example. Obviously, this is not like, as I said, I will show the database partial, just a small part. So here we have disease, symptom, and then information nodes. Information nodes means the sign of symptoms. Okay, so high, low, like fever, high, low, mild, etc. And we, the doctors helped us to create this database, but also we consulted some of the clinical documents which are available for such type of things. Okay. Now, again, the challenges are, I said, how do we store? Where do we store? So that's a major challenge because the graph is very large. If we go for all the, if we develop for all the diseases, then the graph will be very, very large, right? Enormous graph. So where to store the knowledge graph and how to process the data stored in that graph? Okay, so I answered because you see, we are in the kiosk. When we are in the kiosk, our health workers or the patients, they just have small computing devices like mobile phone, smartphone or tab like this, which are energy constrained as well as memory constrained. Okay, so we cannot download such a large knowledge graph in the memory constrained devices. That's not possible. So what do we do? Moreover, we may think, okay, the graph will be in the cloud, and we will first we will send the main symptoms, and then we will get the sign of symptoms, and then we will send the answers, and then again we will get more sign of symptoms. So we will pursue like that. But then again, another challenge in rural areas is poor connectivity. Sending symptoms and sign of symptoms every time to the cloud server and getting back the next set of questions is time consuming. That's not possible, right? So we propose pruning algorithms to get the subgraph based on the input symptoms and download them to the mobile devices, right? So here is the system which was again developed by one of our researchers. So the graph database is in the cloud. The patient visits the kiosk. From here, the patient would first send the symptoms. Okay, the health assistant will ask questions to the patient. The symptoms will be sent through the mobile devices. Here, mobile device will formulate the query, and that query will go to the graph database. From there, queries are symptom-based queries. Okay, from there, a portion of the graph will be pruned. So the subgraph will be downloaded here, and then this here from the health worker will then communicate with the mobile device only and go through the subgraph, and then every time the health worker will ask questions to the patient. Based on the patient answer, these answers will be input to the mobile device through our software. Okay, and then finally, if any preliminary diagnosis can happen, then that will be transmitted to the health assistant. Otherwise, it will be referred to the doctor. So this is the system which we would like to develop. Obviously, we have some part of this, but this, as I said, we didn't focus on preliminary diagnosis, so we didn't do that. So pruning algorithms which we focused on, we developed. The first one was a simple one, BFS-based pruning algorithm. Because you see, we always start with multiple symptoms and we know the symptoms from the beginning, right? So we really do not need very sophisticated algorithms here. And as I said, that the algorithms should be lightweight. So we started with less time consuming. So BFS-based pruning algorithm was used first, multi-source BFS-based pruning algorithm. Secondly, we tried a reachability query-based pruning algorithm, which was implemented with iterative depending depth-first search. Iteratively, it will do the depth-first search and add the nodes to the subgraph as it goes through the depth of the graph. Okay. Obviously, there are other algorithms which can work for reachability query-based algorithms, work as reachability query-based algorithm. For example, Floyd-Warshall algorithm, Thorup's algorithm, that could also be tried, but we didn't try this algorithm. So the idea is, if we have one such graph and the symptoms are say S1, S2, S3, then the graph rooted, the union of the trees rooted at S1, S2, S3 will be pruned and will be sent to the mobile device, will be downloaded to the mobile device. Okay, so now the symptoms are known, the intermediate questions are here, so the health worker doesn't need to go back to or access the cloud every time. He or she can finish asking questions using this graph only and arrive at some preliminary diagnosis, or may refer to the doctor. Okay. We compared our algorithm with one well-known reachability, one well-known algorithm, chain cover pruning. In fact, there is the chain cover algorithm which was converted to chain cover pruning algorithm, and then we tested with a small disease symptom graph and a large disease symptom graph. In each case, because you understand that first one in fact was available. I have shown you the small piece of knowledge base. So using that knowledge base, this could be developed. We got it from clinical documents. But obviously, a graph with 500 nodes cannot be available anywhere. So therefore, this was synthetically developed, and we tried with this graph. And every time we found that the proposed algorithm, that means the reachability query-based algorithm, based on iterative deepening depth-first search, work much better than this chain cover group. That there are reasons also for that, which we explained in our papers. You can go through the paper. This, but pruning or graph knowledge base, this is the work of, in fact, the virtual sensor sensors, all the ideas, all the work, research works were done by Dr. Atri Gupta and Shunando Bose. Shunando just submitted his thesis, and this work, pruning and disease symptom graph, this was done by Dr. Sophie Qureshi Mondal and Shunando Bose and Himadri Shekhar Rai. They have actually worked on the kiosk application. I must mention, because obviously you understand that when after becoming a teacher, it is the students' work, and we are just presenting their work, but obviously the credit should go to the researchers who worked on this particular area. I think someone has asked a question.
Yes, ma'am.
Which notes you said? How notes are selected?
Yes, ma'am. How? Yes, ma'am. How notes are selected randomly? Please explain.
See, we are not selecting randomly at all. As I said, when the patient comes, patient says that, okay, see, I have pain. So maybe pain is symptom 1. Along with pain, it is vomiting. So vomiting is symptom 2, right? So S1 and S2 maybe. Or if the patient says I have fever, fever is say S4. So I should have included one such graph, but I didn't do that. Sorry for that. So say pain is S1 and fever is S4. So then this will be based on the patient's complaint. These two will be selected, right? So when we prune the graph, we will take these 2 nodes, and with these 2 nodes, then we will find the nodes reachable at the next level. So say A, B, C are reachable at the next level. Here N, O are reachable at the next level. Okay. And so A, B, C are the questions, right? That means pain means where? On your stomach or on your head, like that. So this may be headache, this may be stomach, this may be chest, like this. So there are 3. Similarly, fever means fever with cough, fever without cough. There may be 2 questions like this. Okay. So and then so these are the questions, and there are there can be several layers of questions. If you remember, when you go to a doctor asks several questions, right? So whenever doctor asks so many questions, then obviously you give answer. Here we do not give such pressure on the doctor. The questions are here. They come up to the screen automatically. Health assistant, either the patient can automatically give answers, or the patients or the health workers will input the answers. It happened like that. And then so all the nodes reachable from S1 and all the nodes reachable from S4 will be pruned and will be sent to the kiosk, the smartphone and the kiosk. Okay. And then the health worker will work on. Is it clear?
Thank you, ma'am. Participants, if you have any question, you can raise your hand so that you can ask the question directly to ma'am, or you can write down your question in the chat box. I have one question, ma'am. Ma'am, can you explain in kiosk A how you are computing with cloud?
I think I need to go back to, I think this will be, so see this server is at the cloud, right? Here the server is at in the cloud, it is located in the cloud, and all the computation are done here. at the kiosk end, the only thing we do, we are capturing the symptoms and sign of symptoms from the patient. And all those are sent to the cloud here. Okay. Then either from the cloud, those are sent to the doctor, or I explained that using a figure earlier at the beginning of my lecture. So from the cloud, either symptoms and sign of symptoms are sent to the doctor, or maybe from here, some preliminary diagnosis could be done. So two things, I say two things. If it is just question answering, then that is done after pruning the subgraph to the mobile device. Okay, for the question, that means question answering. Why are we talking about question answering? Because we are only gathering symptoms and sign of symptoms of the patients. Rest of the things are done in the cloud only. Okay, so if you have any algorithms to run, if the doctor wants to generate a prescription, then the doctor will have to directly communicate with the cloud. That is what our idea is. Okay.
Thank you, ma'am.
So the next thing we would discuss is health data, big data. Big data definition, this I took from dictionary.com. Okay, I hope this has been discussed in one or any of the sessions which you learned, attended, participated in the previous days. Okay, but still I would like to introduce this. So see, the definition from dictionary.com, it says data sets typically consisting of billions or trillions of records that are so vast and complex that they require new and powerful computational resources to process. Okay, it's a bad definition, you understand, right? It is only talking about billions and trillions. That means volume of the data. We really do not consider only the volume of the data. Big data is not just about size. Find insights from complex, noisy, heterogeneous, longitudinal, and voluminous data. Okay, so it is not just size. So when we want to answer certain questions, just now someone asked me the question, how do you compute, madam, in the cloud? Right, you need to compute in the cloud. But when you compute in the cloud, there are algorithms, machine learning algorithms, AI algorithms. The purpose of my talk is not to discuss the algorithms today, because I understand you have learned the algorithms. But the question, the next question, when we were working with this remote healthcare project, the next question we found, how to store such a huge amount of data in the cloud. You see, I'm not talking just about the disease symptom graph. Disease symptom graph is a knowledge base, but then a huge amount of data is being generated, right? Huge amount of data, this data is related to the patients. The patient's complaint, patients, the testing of patients, sensor data, demographic data, history data. So much data is being generated every time, right? So now how to store the data? So again, the question is health data, how do we think, how do we handle this situation? Is health data big data, right? So you see, I talked about the bad definition. This is also, I could not control myself from referring this particular quotation. Obviously, this quotation may not be related to my talk, but how healthcare is changing, for that one only I wanted to use this quotation. Tim O'Reilly says, how data science is transforming healthcare. For a long time, we thought that tamoxifen was roughly 80% effective for breast cancer patients, but now we know much more. Because now you see personalized medicines are evolving. we know that it's 100% effective in 70% to 80% of the patients and ineffective in the rest. So we are interpreting more from the information. Our information extraction, our knowledge is increasing when we use, when we analyze the data properly. Okay, so if you get and analyze enough of the right data, you can figure out who the treatment will work for. But as I said, really, this is not related to my presentation, but the question which were raised by us, how to store health data. And that is why I am talking so much about this. So obviously, all of us identify health data as big data because it has all these properties: volume, large data sets, variety from different sources, audio files, database records, social media comments, textual data in healthcare we get, like demographic history, demographic data, and family history, etc. Image data like ECG, extra reports, audio data like sound of heartbeat, etc. Velocity, because for continuous monitoring, it is generating very rapidly. E-health sensor data, when you use, the velocity is there, and data needs to be ingested quickly and in some cases acted upon quickly as well. Actions are required for critical cases. Veracity, biases, noise, and abnormality in data. So how to work with such a set of data which has all the properties of big data. I'm not talking about other V's, validity, volatility, etc. So all the data properties are there. We already know healthcare data can be structured, unstructured. We also have genomic data, medical images, behavior data, social network data, etc., mobility sensor data. So all these things are required when we talk about health data. Certainly for our purpose, for the primary healthcare, we only had the data obtained from the patients. As I said, either from the sensors or the data which were input by the health workers. So only we had the those much data, but again they are unstructured. You understand that a person with address, phone number, all these things have are something, and sensor data will be something else. A person visiting a doctor several times will again have variable length of records. So all these problems were there. So we have demographic data, history data, complaint, test and investigations, continuous monitoring of data. This part is almost static, so changes are rare, so can be stored in structured form. Whereas this part is medium static, changes are occasional, contains unstructured data. And this part is dynamic, particularly when we talk about sensor data. Changes frequently and fully unstructured. So we faced several challenges: capturing and representing complex information, integrate the data scattered across many different information systems, how to store the data for quick and real-time retrieval, how to process to extract useful information. Okay, so from this paper, again, I would like to quote this statement: it is necessary to implement syntactical as well as semantical restrictions or defaults to avoid redundant statements or wrong interpretations in complex and or big data sets. So at this moment, we didn't work with provisional diagnosis, or we are not helping the doctors to infer information from the data collected by us. But suppose if we want to infer some information from the data, then we need to process the data, right? And for that, not just syntactical part is sufficient. We also need semantical restrictions. So again, one of our researchers worked with ontology of health data, because ontologies were found to be useful because of the variety aspect of big data. For big data, it has variety, and for that ontologies interpretation, you are actually associating semantics. Big data also make use of statistical techniques for discovery and hypothesis testing. So, and it is a scientific discovery. I should go very fast now. Time, there is not much time. So, ontology-based approaches and big data may help in solving some problems related to extraction of meaningful information. For the time being, the doctors are included in the loop. But suppose doctors are, we want to exclude doctor, then we really need to process the data. So we tried to define an ontology. These are just some examples, some portions of the ontology, like from the person. We have non-healthcare worker, healthcare worker. Then we also have doctors, lab technicians, nurse, etc. I'm just going to the ontology. And also, whenever you develop an ontology, one basic understanding is you must reuse the already existing ontologies. So many of the parts like person and then information entity, thing, all these things, many of the ontologies, existing ontologies we have reused. Right here, we had to introduce some thing. For example, preliminary diagnosis here. So vital signs. So it's not possible to explain all the terms here, but the ontology was required, and the main aspect is we are working with this particular work. Can we generate the schema, database schema? Because you still see we are for developing relational databases, that means structured schema, we have certain rules. If we have, whenever we go through the RDBMS, relational database management system, we had to study certain rules, right? But when we work with unstructured databases, we really do not have some rules like that. So our current research work is on based on ontology and a set of queries. And our question is, can we propose some algorithms so that this can be translated to a big data schema? We are trying this, okay? So some works have been done, not entirely, not complete yet, but some of the ontology-based works have been, and this was the work of Polly Shilshed, and some were published in different conferences. Now the last part of my, so actually the last part of my talk is uncertainty. Again, I will go through this very quickly. So as I said, if we work with sensor data or just data which were input by health workers, we can face uncertainty in data due to missing data, maybe due to erroneous data, right? So we will mainly focus on sensor data, type of sensor data. I mean, what are the different types of sensor data? So these are the questions. What caused the data error? When manifested? Where located? When observed? How does it propagate? What functionality does it affect, and to what degree, right? So the error can be biased or random, intentional or unintentional, whether the error varies with time, measurement error or usage error, sampling or approximation error. If you approximate something, there can be certain errors. And also there can be, because we are talking about sensors, there can be interface errors caused due to electrical or mechanical failures. In our work, we mainly considered random error because we found random errors are more dominant for in-sensor data. How to, so our questions were, our challenges were how to use sensor data prone to random errors, how to produce acceptable output if large number of samples are not available. See, I cannot ask patient that I should take measure your blood pressure 10 times and then take the average of it. That's unacceptable. If you, even in the hospital environment, if the nurse says that I will measure your blood pressure twice or thrice, then obviously you will be very annoyed, right? So we have only limited number of samples. Again, the lightweight model, because we cannot allow much computational time for this. Decisions should be made very quickly. Okay, so these were our focus. Now, before doing this work, we did some preliminary analysis. What we did, we we actually send our students to a puja pandal, you know, and in the puja pandal, the students were equipped with a blood pressure sensor with a device which normally the blood pressure, digital blood pressure sensor and a analog pressure checking equipment, right? And and we made for every person who entered the puja pandal, they were eager to check their pressure. So we checked the pressure using two devices, and whatever data we got, we plotted like this. You see, we checked. There were 200 data we gathered like this, and you can see the chart. These are blood pressure. So we have two parts: systolic and diastolic, right? Analog systolic and analog diastolic, and digital systolic and digital diastolic. From this, you can see that there is no bias. We assumed that the analog device is correct. Okay, so you see there is no bias. Basically, the errors are random. You can see from here also, this is the error distribution. The error is random and limited, and most of the errors are within a very narrow range, but there are other errors outside this range as well. Okay, so we used we actually used two techniques. The first one is fuzzy system map modeling, and the second one is interval mapping. And two use cases were used. The first one is keywords and single sensor. And keywords means, say, hypertensive. A person is hypertensive. With this knowledge, we check whether our sensor is giving correct data or not. I mean, there may be two things. When we check the blood pressure for a hypertensive person and we get a normal value, then either the sensor is erroneous or the person is recovering, right? Both can happen. So we use keywords and single sensor and multiple sensors of different types. But these two use cases, which I am going to explain, I mean, I don't have to explain for a longer time. I'll finish very quickly. But these two are specific for these two cases only, blood pressure and the other one is fever. Okay. If you have other types of sensors, other types of diseases, then obviously you will have to think it differently. So these are the vital minimum and maximum limits of vitals which were given to us by our doctors. So in the first use case, there are two steps actually. We first map the values into three fuzzy linguistic values, like systolic and diastolic, high, low, and normal. And also these are the output. These are the input and these are the output. Outputs are also normal, possible error, and error. For example, as I said, for a hypertensive person, if the systolic blood pressure is low, that means this is an error. Okay, and if it is normal, then we can say it is possible error. So we will have to go to step 2 for checking. And we designed this rule base for checking in the first step. And in the second step, actually, in the first step, we just filter out the error values. In the second step, we just check the possible erroneous values. And for that also, we have devised a rule base. And we also have the input as well as output here. So actually using fuzzy modeling, we did this one. Because the time is up already, 1 minute extra. So I'm not going to explain more. As I said, you can read the papers. In the second case, that means the second use case, here fever is identified. Again, fever can, I mean, if the temperature is high, that can be due to the sensor error, or the person may have real fever. So we are using two sensors, temperature and pulse. And based on these two input data, we have devised the rule base, and the acceptor is the output. Okay. And if it is not error, then you can filter out those values. If the person has fever, then obviously you can refer to the doctor or do something. So all these things are required when actually the person is remotely located, and this is not for the kiosk based software. This is particularly for continuous monitoring. At the beginning of my lecture, I said that I will consider all these use cases. So such type of whatever I have discussed in the last part of my talk, that is for continuous monitoring of the patient, or even in the kiosks, these techniques can be applied. We can think about that also, right? And this I mentioned another technique, interval mapping, but I'm not going into those details. This uncertainty recognition is the work of Dr. Atri Gupta. So she has done something on not just uncertainty removal, but also prediction of missing sensor data. Okay. So to conclude, health data is not only voluminous, but also has other properties of big data. And there are several aspects. In fact, throughout my lecture, I really tried to give you some experiences, to share with you some experiences which we encountered while working on our project. And I think that these challenges and issues need to be handled further, so that we can come out with a very good, sophisticated IoT-based system for primary health care in our country, because our country is an underdeveloped country, and we really have so much problem in rural areas. And so we need to focus on these problems. In fact, I didn't discuss today, but there are other works also, like how do we work with, say for example, if we do not have internet, how can we send all the symptoms, etc., using SMS? Okay, so there are other works also which are based on the issues we encountered while working on our project. Okay, so I focused on few different things, but if you consider implementation of a telemedicine sort of software based on sensor, cloud, and mobile technologies, then obviously all these challenges will have to be considered, and issues will have to be overcome, handled properly to be successful in the telemedicine domain. Okay, remote health domain. Okay, thank you very much for listening to me.
Thank you very much, ma'am, for extremely illuminating session that you have shared with us. Now, with due permission, I will be taking some questions from our participants. We have got two raised hand from two participants. One of them is Dilip Kumar Koda.
Yes.
Prem Kumar, can you please unmute Dilip Kumar Koda so that he
Yes.
can ask the question
Yes, ma'am.
to ma'am?
Dilip Kumar Koda, sir, you can just switch on your mic and you can ask a question to ma'am directly. Dilip Kumar Koda, sir, you can switch on your mic. Sir, are you able to hear from us? Dilip Kumar Koda, sir.
Maybe by mistake,
Okay.
yes.
Yes, yes. So we move on to the next participant, Shubroto Dotto. Please unmute him, Prem Kumar.
Sir, you may switch on your mic.
Yes, am I audible, ma'am? Am I audible?
Yes.
Yes. Okay. So, ma'am, I want to know that how this pattern mining and rule mining technique can be used for this handling this voluminous healthcare data. Can it be formed in some kind of inference rules?
Pattern mining and rule mining. See, rule mining, I should not say that, I mean, certainly in some cases this can be done, but you need huge amount of data, how the doctors have actually taken decisions in certain cases. Unless we get that data, like say for example, if we have several X-ray image, chest X-ray images, huge number of chest X-ray images, okay, and along with that, the prescriptions of the doctor for in each case. If you have that, and also the treatment history in each case, if you have that, then possibly, I mean, this is not my domain, but I think then possibly you should be able to apply some rule mining techniques or pattern mining techniques in such cases. But as you understand, getting so far, our, I mean, we are not, we do not store health data properly. We really do not have that system. And all the hospitals have different systems, and they do not want to share the data with the researchers also, always. In some cases, obviously, the researchers are fortunate enough, but in many cases, they cannot do that. So in those cases, data is really a problem, getting data. We also tried a lot, but from the kiosk, whatever data we have generated, we have used those. But other than that, we were unable to get data from the hospitals. Okay. So if you get that data, then you can incorporate such type of techniques. I think that would be very useful.
Yes. Yes. Thank you, ma'am. Thank you, ma'am.
Ma'am, myself, actually, I've already asked one question, but that was not related to algorithm. Actually, I want to know regarding on that kiosk. That is, you told okay. So I need some suggestion from you that how fast data we can store in cloud. Actually, for real time in fast session also, I have asked this question. Actually, how we can realize the real time, or we can visualize the real time signal. That means we want to store the data, or say not store, actually send the data, and similar at the same time we want to visualize from the world in another side point of view. Suppose PCC signal or maybe ECG signal, and I want to that send it in cloud 1 kilohertz frequency rate, and similar way you can visualize direct real-time signal from your mobile. So is it possible that kind of server? Actually I am asking for?
There will be some delay, as you understand, obviously, if you try to visualize at the same, there will be some delay, but the what I think the delay would not be much. Okay, we tried with this, maybe, but we tried not, I mean, in such area, it depends again on the internet bandwidth, internet speed, everything. So I cannot say it is 10 millisecond or it is 1 second or it is 10 second. Such type of measurement I cannot say, but it is possible to visualize at the same time. Right? At the same time means maybe with a delay of say 10 seconds. Right.
Okay,
I'm
ma'am.
just saying, but just like
Actually,
when
in a
you
different
browse
server,
something.
trying, but we are trying. Actually,
Hmm.
myself, I am trying, but
Hmm.
whole data that is not it's uploading and not visualizing. Just for few seconds, or 1 or 2 seconds, it is visualizing from mobile. So that's why I'm asking you regarding on that server. You were telling that, or
Which
saying that
server have you
server.
tried? Which server have you tried?
Normal server, ma'am, Amazon, or maybe that is a MathWork.
I can give you. I mean, if you just
Cloud.
mail me, my email address may be obtained from this MacOut. I mean, professors of MacOut, Professor Suparna Bishash or Professor Rupali. But I can write in the chat also. So I can give you some of the server addresses which my students they have used. Right, I am writing my email addresses. If you write,
okay, ma'am, I'm taking
then
that
I
email.
can.
And actually, ma'am, I am from NACC. So if you say I can, also I'll mail you because in from Guria near Jadavpur.
Okay, so this is my email address. So if you send email, I can say I will be able to send some of the servers which were used by by the researchers who worked under me. Okay.
Okay, ma'am. Okay, thank
And
you
we
very much.
measured also. So in some cases we measured also. I don't have the data at this moment in our hand, but you can. That can be. I mean, the delay is not enormous. That can be done.
Okay, ma'am. Okay, ma'am. Thank you. Thank you, ma'am.
Thank you, ma'am. Pramod Pal, do you have any question to ask to ma'am as you raised your hand? I don't think he mistakenly raised his hand.
Pramod Pal, sir, if you have any question, then you may ask your question, sir. Pramod Pal, sir, we are not able to hear you, sir. Ma'am, I think there is some internet issue.
Okay.
Yes.
You may continue.
Okay. So participant, as we are already running out of time, so if you have any further questions or queries, then you can email ma'am, as ma'am has already shared her mail ID in chat box. You can note it down for your reference. And thank you, ma'am, for sharing your practical experiences of working on working on a remote health project. That was extremely illuminating. And as I would like to say something like healthcare domain has been always flooded with a lot of information that are generated through different sensors, but through your lecture, through your session, we learned that processing, storing, and efficient retrieval of those data in real time is a very much crucial thing. And not only that, I mean, whatever data we get, we have to get the correctness of the data. That means overcoming the uncertainties of the data that are generated through erroneous sensors using AI. So this has been very elucidating talk. And we are really privileged to have you with us, and we hope we will get you in future in our university's program as well. And thank you, ma'am, for sparing your valuable time with us. Thank you.
Thank you. Thanks to all of you, all the participants, and both of you.